Hello, and welcome to the Live Lab. This is the space where we'll be using our system Neon in a live study happening next week. Our system performs multi-person eye tracking in dynamic real-world scenes. Current eye tracking methods are limited to single-person controlled settings, such as through a laptop webcam. Our system is the first of its kind to be able to do multi-person eye tracking in a dynamic scene, such as a concert which will be held here. Our system processes up to 30 streams provided to us by devices called Neon glasses, which look like this. Our system records and monitors in live time these 30 streams, as well as a stream from the central camera of the stage. After the recording is complete, we then perform a projection of every gaze onto that central video. And the final output of the system is this video with all gazes projected onto it. So at any point during the recording, we can see exactly where each of the 30 participants was looking at any point in time. This allows for interesting research in the neural, audio, and visual space. We can record up to 30 devices without direct access to the devices in a remote setting such as from the control room, which you can see here. I don't have direct access to the devices. Before recording, we assign static IPs to each device, so we know exactly which IP belongs to which device on the network, so we can connect directly to all of them or to a subset of them. Our script listens for key presses. So first, we're going to start by starting recording on device number 8, which has the following IP. As you can see, recording has started in a remote way. I don't have direct access to that device. During recording, we can do a variety of different things to check the health of the recording, such as checking the status. Using the M key, we can check status and again input the IP, and we can see that we have a valid recording ID and a valid hardware, which means our devices are connected and they're recording. We can also remote restart the Neon application in case of a failure. So first we're going to stop recording on the device by again using a key press and inputting our IP, and then we're going to restart the phone by inputting its IP. And as you can see, the phone is remotely restarting. So as you can see, the app restarted on this device. Once the recordings are completed, they're automatically saved to the pupil cloud, from which they can later be pulled for offline analysis.
For monitoring the health of our system, we created architecture using Kafka, FFmpeg, and Grafana. This is how our pipeline works. First, we connect to each phone's video stream over RTSP and decode the individual frames with a custom build of FFmpeg using hardware acceleration. Once the frame is decoded, it is then timestamped and sent to Kafka to be later on used in our dashboard service. Our dashboard service captures this frame and displays it. Our dashboard is intentionally capped to 1 FPS for performance reasons when scaling up to 30 glasses. On top of frame data, we also collect other metrics based on the health of our system, such as how backed up our system is, as well as how much data is flowing through Kafka at any given time in a time series graph.
The core of the homography module is the computation of the homography matrix, which essentially tells us how we can relate two views by a projective transform. So for us, the matrix tells us how we can translate or transform the glasses perspective to match up or align with the central scene view, regardless of where the participant is sitting within the audience, and how they have their head tilted one way or another.
To produce the homography matrix, we first need to relate the two views. To do so, we use a deep learning model called SuperGLUE, which identifies the key features for each perspective and finds strong matches between them. These matches are the key points that appear in both views, which become the inputs for the homography matrix computation. It is also critical that we properly timestamp match the glasses perspective with the central scene view, so we're performing the homography between the two frames that occur at the same time. With the homography matrix computed, we can then transform the gaze coordinates for each frame to see where they would lie on the central scene view, giving us the final video output with all the gazes layered on.
This project was developed by
Biranugan,
Mehak, Areez,
Neil,
Zahid. Our project was used in a research study happening here at the Live Lab at McMaster on April 2nd and 4th. Keep an eye out for a research paper written by our supervisors Shreshth and Dr. Lobo and Fink, which will involve us and our contributions to the project. Thank you for watching our capstone video.